Good evening one and all. Welcome to Design of Machine Elements Learning Series, Series 3, Selection of Materials, Material Properties and BIS Designation of Steels. The objective of this presentation is to understand the importance of selection of materials, the significance of material properties and the BIS designation of steels. Selection of an appropriate material for a component or a structural member is an important decision in a design process. As a design engineer, you should consider the following points, that is, study of material properties, availability of raw material and economic aspects. The study of material properties include the study of chemical, physical, mechanical, dimensional and technological properties. Availability. It is an important factor in the selection of the raw material because the material should be readily available, especially in large quantities. Cast iron and aluminum alloys are always available in large quantities and there is a shortage of lead and copper alloys. As a mechanical design engineer, it is important that you ask the following questions before the procurement of the raw material. First, is the material available in hand? If the answer is no, can we get it in 1 to 2 weeks? If the answer is yes, how much quantity of the raw material is required? Second, what is the nature of suppliers and how many suppliers are available? Third, is there any special method required for fabrication of the raw material? If the answer is yes, then the designer needs to establish timeline for procurement. Economic aspects. Cost is used as a prime factor for selection. The cost of the material of a mechanical component consists of initial cost, processing cost and maintenance cost. Here are few guidelines which a design engineer can refer to before doing a cost analysis. Labor and material cost always show an increasing trend. Cost of processing shows a decreasing trend due to use of automated tools and robots, and cost of manufacturing of a single component or a product varies from city to city and from one plant to another due to overhead, labor, taxes and freight differences. Mechanical properties of engineering materials. The mechanical properties of an engineering materials which a design engineer should consider while designing a product or a component are strength, ability of the material to resist without rupture due to external force causing various types of stresses, elasticity, ability of the material to regain its original shape and size once external forces are removed, plasticity, ability of the material to retain its deformation produced under the load on permanent basis, stiffness, ability of the material to resist deformation under the action of external load, resilience, ability of the material to absorb when deformed elastically and release energy when unloaded, toughness, ability of the material to absorb energy before fracture takes place, malleability, ability of the material to deform to a greater extent before the sign of crack when subjected to compressive force, ductility, ability of the material to deform to a greater extent before sign of crack when subjected to tensile force, brittleness, property of the material which shows negligible plastic deformation before fracture takes place, and hardness, that is the resistance of the material to penetration or permanent deformation. Classification of engineering materials. Engineering materials are broadly classified as metals and non-metals. Metals are further classified as ferrous alloys and non-ferrous alloys. Non-metals are further classified as glass, plastic and rubber. Ferrous metals or ferrous alloys. Cast iron. Cast iron is a 4-element alloy containing iron, carbon 2 to 4%, silicon and manganese. Cast iron is further classified as grey cast iron, ductile, that is nodular cast iron, white cast iron and malleable cast iron. Grey cast iron. Grey cast iron is grey in color due to presence of graphite. It has good compressive strength and wear resistance. It finds its application in gasoline and diesel engine blocks, machine bases and frames, gears, flywheels, brake discs and drums. Ductile or nodular cast iron. When ductile cast iron is alloyed with magnesium, it causes formation of nodules. Presence of nodules gives its sustainable ductility with improved tensile strength, stiffness and impact resistance. It finds its application in engine crankshafts, heavy duty gears, hardware items, etc. White cast iron. This particular cast iron is white in appearance because of fractured surfaces which are produced due to chilling in the mold. The structure is extremely hard, wear resistant and brittle. It finds its application in ball mills, extrusion dies, cement mixer liners, railroad brake shoes, to name a few. Malleable cast iron. It is obtained by two-stage heat treatment process and it is used for heavy duty applications. Steels. Steels are broadly classified as plain carbon steels, alloy steels and iron-based super alloy steels. Alloy steels are further classified as high strength low alloy steels, that is HSLA, case hardening steels and stainless steels. Non-ferrous alloys. Non-ferrous alloys are aluminium alloys, copper alloys, magnesium alloys, nickel alloys and nickel-based superalloys, titanium alloys and zinc alloys. Non-metals. Non-metals are broadly classified as plastics, natural rubber and synthetic rubber. Plastics are further classified as thermoplastics which soften due to heat, thermosets which do not soften due to heat, and fiber reinforced plastics which is a type of composite. Natural rubber. It is a low cost elastomer. Natural rubber is found in hard and semi-hard condition and it is used for belts, bushes, flexible tubes and vibration mounts. It is also used for production of coatings, protective films and adhesives. Rubber coatings provide protection in a chemical environment. Synthetic rubber. Synthetic rubber has properties similar to natural rubber. They are thermoplastics or thermosetting plastics. They are costlier than natural rubber and find applications in conveyor and V-belts, brake diaphragms, gaskets, seals and O-rings. BIS designation of steels. Steels are designated by a group of letters or numbers indicating any one of the following three properties: tensile strength, carbon content and composition of alloying elements. Steels standardized on the basis of strength. Steels are designated in the following two ways. First, Fe followed by minimum tensile strength in Newton per mm square and Fe capital E followed by minimum yield strength in Newton per mm square. Let us study the following examples. Fe 320 stands for steel with minimum tensile strength of 320 Newton per mm square and Fe capital E 400 stands for steel with minimum yield strength of 400 Newton per mm square. Here we should remember that whenever the designation has capital E, it stands for minimum yield strength, and when there is absence of capital E, it is minimum tensile strength. Plain carbon steel. Designation of a plain carbon steel: a number indicating 100 times the average percentage of carbon, a letter C, and a number indicating 10 times the average percentage of manganese. So 55C4, 55 is the number, divided by 100, that will give you the percentage of carbon. 4 divided by 10 will give you the percentage of manganese. 30C8, 30 divided by 100, that is 0.3% carbon, and 8 divided by 10, that is 0.8% manganese. So let us now designate the following plain carbon steel whose chemical composition is given to us. So that is 0.4% carbon and 0.8% manganese. So 0.4 multiplied by 100 will give you carbon, that is 40C, and 0.8 multiplied by 10 will give you the number 8. So the designation of this particular plain carbon steel whose chemical composition is given to us is 40C8. Designation of unalloyed free cutting steel: a number indicating 100 times the average percentage of carbon, a letter C, a number indicating 10 times the average percentage of manganese, and a symbol of the following elements depending which make the steel free cutting, and a number indicating 100 times the average percentage of the above elements. So let us understand the designation of unalloyed free cutting steel. 25C12S14. So 25 divided by 100 as per the first statement gives you the percentage of carbon. 12 divided by 10, that is the percentage of manganese, and 14 divided by 100 will give you the percentage of sulfur, which makes the steel free cutting. Designation of alloy steels. The term alloy steel is used for low and medium carbon steels with 10% alloying elements, a number indicating 100 times the average percentage of carbon, and a chemical symbol of alloying element followed by a number for its average percentage content multiplied by the factor given below in the table. So this table gives you the different alloying elements towards the left and their respective multiplying factors. Elements and multiplying factors. Now point to be noted that the symbol of manganese will be included only if the content is greater than 1%. Now let us understand this particular designation. 25 Cr4MO2. So as per this first statement, 25 divided by 100 will give you the percentage of carbon. Okay. What is the digit after chromium? It is 4. So in order to calculate the percentage of chromium, you have to divide this digit by the multiplying element. So where is this chromium? It is in the first row. So 4 divided by 4 will give you the percentage of chromium. In the similar manner, to calculate the percentage of molybdenum, that is 2 divided by 10 will give you the percentage of molybdenum, that is 0.2% molybdenum. Now designate the following steel. Carbon 0.12 to 0.20%, nickel 0.6 to 1%, and chromium 0.4 to 0.8%. So what is the average percentage of carbon? 0.16 multiplied by 100. The average percentage of nickel, we will get the average as 0.8, 0.6 plus 1 divided by 2, multiply by the multiplying factor. The multiplying factor for nickel is 4. So 0.8 multiplied by 4, that is 3.2, approximately 3. Now average percentage of chromium will be 0.6 multiplied by 4. Now from where did we get this 4? We got it from the multiplying factor. So that is 2.4, approximately 2%. So the complete designation will be 16 Ni3Cr2. Designation of high alloy steels. The high alloy steels are designated as follows. Letter X, a number indicating 100 times the average percentage of carbon, a chemical symbol of alloying elements rounded off to the nearest integer, and chemical symbol to indicate specially added elements. So X15Cr25Ni12 stands for 0.15% of carbon, that is 15 divided by 100, 25% of chromium, and 12% of nickel. Designate the following high alloy steel whose chemical composition is given to you. So carbon 0.15 to 0.25%, nickel 1.5 to 2.5%, and chromium 16 to 20%. So the average percentage of carbon will be 0.2%, that is 0.2 multiplied by 100, that is 20. Average percentage of nickel will be 2%, and average percent of chromium will be 18%. So the designation of high alloy steel will be X20Cr18Ni2. The following presentation is made by using the following references. Design of machine elements by K. Ganesh Babu and K. Sridhar. Design of machine elements by V.B. Bhandari, and Machine Design Fundamentals and Applications by P.C. Gope. Thank you very much and wish you a